All right, hello and welcome everyone to my 16.6 pre-class video. For this video, I decided to go back to kind of my old set of class notes here. And I want to do some problems from these notes. So these are notes that normally I would have done in class, and I thought they would make an excellent pre-class video for us. But just kind of a heads up for everyone. There are some pre-class videos that I made some time ago. They're at my website, MTH234.com. These are for the chapter 16, section 6, and it talks a little bit about parametric surfaces. And you can see that this is just what I went over in there. So if you're interested in watching these, I think this is really a nice introduction to the subject. As you can see here, this is going to be upgrading instead of a parametric curve. We're going to be talking about a parametric surface. So with a parametric curve, right, you can kind of think of these as like strings and stuff like this, some interesting space curve. And in their heart, they're one-dimensional, right? They have length and stuff like this, but they don't really have like width. And so that makes sense, right, that there's one variable, one parameter, t. If you wanted to upgrade this to something that has length and width, you know, something that's two-dimensional, of course, you probably are thinking, well, I would like to have another variable at hand. And so this is where the s's and the t's come in. When you read about this in the textbook, they like the parameters u and v, which is perfectly fine. So instead of s's and t's, you can use u and v's. And so we'll probably be switching through this, and you'll see in your web work homework, sometimes we use s's and t's, sometimes we use u's and v's. Sometimes we don't use any of those, right? I mean, anything can really be used as a variable. But those are kind of the most common ones. And then we do this parametrization here. Okay. So on to the new stuff. So yeah, if you'd like to watch that video, please pause this one, go do that, come back. Let's go ahead and do a few more problems. Again, kind of we're very interested in writing this surface. So here we have a nice surface, you know, as a parametrized surface. So this is z equals 3 root x squared plus y squared, all under that square root there. And if we play with this a little bit, right, you can see that maybe we make this like z over 3 is equal to the square root of x squared plus y squared. And then you can imagine we square both sides. Z squared divided by 9 is equal to x squared plus y squared. And now at this point, you should say, this looks familiar, right? This is something that we did back in our 12.6 days. This right here was the exact setup for a cone. So this right here is going to be a cone. Let me go ahead and maybe draw just a regular old cone here. Cones go on forever in both the positive and negative direction. But you can see if we started working backwards and we're just graphing this one right here, right? Normally when we take the square root, we would have to have the positive square root and the negative square root. But here we only have the positive square root. That means that this is only going to be spitting out positive z values. And in particular, this restriction right here tells us that, in fact, it's only going to spit out the z values between 0 and 3. So instead of an infinite cone going on forever, this is only going to be a cone that spits out the positive z values between 0 and 3. So maybe something like this. And this right here is what we would like to parametrize. So often when I'm trying to parametrize something, I try to think about what is the best coordinate system for the surface? What does it look best in? And in this case, I would like us to all agree at some point anyway, that the answer for this one is cylindrical, that I think that cones really look nice in cylindrical coordinates. Let me maybe convince you a little bit of this, right? First of all, spherical is kind of out on this one. I see this x squared plus y squared, but I don't see a plus z squared, right? So I can't transform this into spherical so nicely, right? I can't transform this into like rho squared or anything like this. But if I think about transforming this into cylindrical, then this just becomes z equals 3 square root of r squared. Now, r is going to end up being a nice positive number. That's how we take it. So the square root of it squared is just going to be 3r, right? And this looks quite nice. And so that's why I'm very interested. Again, cones, I mean, you can kind of do them Cartesian with x's and y's, but this doesn't look particularly beautiful. I think z equals 3r is the cleanest that this looks. And so usually by following this line of thinking, you get a really nice parametrization. So let me show you what we get if we do this for our parametrization. All right, so if I'm thinking cylindrical, then thinking about x, y, and z, x would be r cosine theta, y would be r sine theta, and z is just z. But now remember, we only get 3 variables, and moreover, we would really like these to be, the variables here to be s's and t's, right? So this is specifying our variables here should be s's and t's. So, okay, let's go ahead, instead of r and theta, let's use maybe s cosine t. Let's use s sine t. And then from z, remember, this isn't just any old random z. This is the z that is the height of this cone. And so again, we have this over here, and we already did a little bit of work, and we saw that z is equal to 3r. Now in this case, my r is being taken, and we're using s instead. So I'm going to go ahead and write 3s. So right now, my parametrization that I'm thinking about is r of st is equal to s cosine t, s sine t, and 3s. And that's just about all there is to it, except for whenever you come up with a parameterization, it's always best if you go ahead and you list the domain for your variables. And so in this case, right, they do not go on forever. In fact, theta, or our t in this case, will hit all of the points when we go from 0 to 2 pi. And then s, I'm going to go ahead and I'm going to write down something that's wrong here, right? So I see up here that we have z ranges from 0 to 3, so I think maybe s, right? S should range from 0 to 3. And again, this isn't quite right. And so I'd like to maybe pause for 30 seconds. I'm going to take a drink of water, actually. Let you think about it. What's wrong with this? And then I'll tell you, I'll spoil the surprise for you. All right. So here it is up here, right? Z is equal to 3R, or down here, Z is equal to 3S. So if you try to figure out what is the corresponding S range, well, if you plug in 0 for Z equal to 3S, well, then you get S equals 0. So that's perfectly fine. But on the upper end of the range, right, when Z is equal to 3, and again, Z is equal to 3S, then that gives us the equivalent S is equal to 1. So the upper range here should be S is equal to 1, because once S hits 1, or this radius hits 1, we multiply it by 3, and this is going to give us the Z value of 3. So this right here is our final answer. This is how we could rewrite that cone as a set of parametric equations. All right, let's go ahead and do another one. Find a parametrization for this surface here. And of course, we could look at this and we say, that's a sphere. And very similar to the last one, right? I'm going to think about, okay, what coordinate system do I think a sphere would look best in? And of course, the answer has to be spherical, right? Excuse me. Spherical is what's going to work very well for spheres. And so, I mean, I could draw a little picture here. This is a sphere of radius 3. Something like that. Not the best sphere ever, but fine. We can also rewrite this, right? This is the same thing as rho squared is equal to 9, or rho is equal to 3. Quite literally, the 3-dimensional radius is 3. And so let's go ahead and try to find a way to parametrize this. So again, I'm thinking spherical. So when I'm thinking spherical, and by the way, whenever I think spherical, I always do a kind of 2-step thing, right? Because I have a hard time sometimes remembering all the transformations. And I know on an exam or whatnot, you get a formula sheet and that'll help. But if it's on a quiz or something like this, where I'm just trying to remember, usually I take a pit stop really quick in cylindrical. So I do r cosine theta. And then I remember one triangle here, just this one. So thinking about, this is the positive z-axis, and this is some angle phi coming off of the positive z-axis, and this is my rho here. Then this right here would be my r, my 2-dimensional radius stuff. And so I can do that here in order to figure out the equation for r in spherical. So this is going to be rho sine phi. And then, of course, the cosine theta is just kind of along for the ride. So again, what I'm doing here in order to get this So I'm looking at this triangle, right? This is a nice right triangle. And so I remember this triangle all right. And in this case, right, I want to get something, I want to trade in that R here. And so I'm thinking, okay, well, let's use sine, right? So if I write down sine of phi is equal to the opposite, R, divided by the hypotenuse, rho, right? So the rho, the only thing that's not really spherical in this equation is this R. And so if I go ahead and I rearrange this and I bring the rho over to this other side, that's where we get that R is the same thing as rho sine phi. So that's just how I kind of remember this here. Likewise, for y is r sine theta. And we now know that r is the same thing as rho sine phi in spherical. Oops, that's supposed to be a sine theta there. And then z. Well, z is right here. And so that's the adjacent side. And so if I was to use another one of these equations here, cosine phi is equal to adjacent z divided by hypotenuse rho. And move this around a little bit, we're going to get z is equal to rho cosine phi. So a couple issues, right? First of all, I have a total of 3 variables. I have rhos, I have phis, and I have thetas. I'm only allowed to get 2 variables, right? S's and T's. So I have to figure out how can I get rid of one of these variables. And the way that we're going to do this is, well, excuse me, we know that we're on the sphere. And so when we're on the sphere, we know that rho is equal to 3. So I'm going to go ahead and swap it, and everywhere I see a rho, I'm going to put a 3. Let me also, at this point, I'm going to change t to be theta. So instead of thetas, we're going to be writing t's, and instead of phi, we're going to write s's. And that'll give us our parametrization. So let's go ahead and do it. R of st. For x, we're going to have 3 sine phi cosine theta. And again, instead of phi, I'm writing s. Instead of theta, I'm writing t. All right. For our y variable, we have rho sine phi sine theta. And then finally, for our z, we have rho cosine phi. And again, whenever we come up with a parametrization, we'll always list the domain for our parameters, for our s's and for our t's in this case. So t theta from spherical coordinates goes from 0 to 2 pi, and phi from spherical coordinates goes from 0 to pi. So if we're interested in getting the entire sphere, that's how we're going to do it. Those would be our bounds here. And okay, just kind of a quick remark here. If it heads up, right, if you're doing things right, then often your bounds for your independent variables, whether those are s's and t's or u's and v's, should not really depend on one another. This is a decent rule of thumb. I mean, certainly there are counterexamples and all that sort of stuff, but you can see that you get nice constants. So t is 0 to 2 pi, doesn't rely on s. S here is 0 to pi, doesn't rely on t, so they're independent from one another. Excuse me. All right, 2 problems down. I was going to do one more here for us. So in this problem here, we're going to have some conflicting information, and I want to show you how to deal with this. So first of all, let me do a quick sketch. So we have this nice tilted plane here, and we want, again, this probably goes on forever. You know, like many curves and many surfaces out there, they go on forever. But we only want a piece of this, right? We want the piece that lies inside of this cylinder here. And so let me do a quick picture here. In fact, let me change colors. So for the cylinder, we'll do green. This is basically just a circle of radius 2. And then as you can see, it doesn't rely on any z coordinates. So that same circle is just kind of at all different z values. Circle of radius 2. And then we're going to have a nice tilted plane. So maybe something like this. Of course, these things intersect. And you're going to get something like this. And again, we want the piece of the plane. So the surface itself is the plane. And then there are some bounds, right? It says we don't want the plane to go on forever. We want only the piece that lies inside of the cylinder here. And so that's what that's being used for. It's not really the surface, right? The cylinder is not the surface. It's just used to cut the surface, right? And tell you where should we care about the plane. Oh, guys, we have great news here. My cat has joined us. This is Crookshanks. She loves to flop on my keyboard sometimes. Isn't that right? Yeah, she says, I don't want to be held right now. All right. So maybe you already see the conflicting information, right? Planes look great in Cartesian. There it is. X's, Y's, Z's. I'm perfectly happy with a plane in Cartesian. I wouldn't necessarily want to see it in cylindrical or spherical. And then we have a cylinder, right? Cylinder, this looks great in cylindrical. Easy to believe, right? And so the question is, well, should I parametrize with Cartesian coordinates or should I parametrize with cylindrical coordinates, right? Because there's kind of two different things pulling me in different ways. Excuse me. And the answer is cylindrical. And so let me give you a nice little rule of thumb. You should parametrize to your boundary. So, well, I'll say use the coordinate system that resembles or somehow encaptures, right, looks best in the boundary. Not necessarily the surface itself. All right, so in this case, we're going to use cylindrical, right, because our boundary is a cylinder here, and you'll see that this turns out quite nicely. So when we do this, we've used a lot of S's and T's. Let's go ahead. I'm going to give my parameterization with U's and V's this time. So I'd like to come up with a parameterization R of UV. So our parameters here are going to be U's and V's. All right, so again, normally for cylindrical, X would be equal to R cosine theta. Y would be equal to R sine theta. And Z would just be equal to Z. And so in this case, we're going to use U's and V's. So I'm going to do maybe instead of R, I'll do U. And instead of theta, I'll do V. If you would have switched these around, it wouldn't be a big deal, right? I mean, maybe your bounds and everything would be a little bit different, but you could still get a perfectly fine and 100% correct answer, right? Even if you switch your U's and your V's, or in the last examples, if we were to switch our S's and our T's. All right, here we have U sine V. And again, we have to get down to just having U's and V's. So we have to say, well, how do I get this Z, right, in terms of U's and V's? And that's where we need to use that, right? This isn't just any old random Z values, right? But these are the Z values that are on this plane. And so let's go ahead and maybe rearrange this. I'm going to try to squeeze it up here. I'm going to have 5 minus X plus Y. That's equal to 3Z. And so now I just need to divide by 3 everywhere. So let's go ahead and do that down here. So Z is going to be equal to 5 minus X plus Y, all divided by 3. And now remember, X, we know a parameterization for that in terms of U's and V's. It's this right here, U cosine B. And Y, we know a parameterization for that in terms of U's and V's. It's this right here. So we can parameterize Z, now that we have it in terms of X's and Y's, by just plugging these in. So we're going to have 5 minus X, so that's going to be U cosine B, plus Y, U sine V, divided by 3. All divided by 3. There we go. All right, so this is essentially our parameterization. Let's go ahead and write it down. R of uv is equal to x u cosine v, y u sine v, z 5 minus u cosine v plus u sine v, all divided by 3. Pause for 30 seconds. Think about what should your bounds for your parameters be. All right, let's talk about it together. V's are taking the place of theta. So this should be from 0 to pi. U is taking the place of r. So again, our radius doesn't go on forever. Let's go back up here, and we can see that our radius stops at r equals 2. So it ranges between r equals 0 to r equals 2. All right, this right here would be my final answer. Oops. All right, I hope you guys found this useful. Thank you so much for watching. I'll see you next time.